Good. You can see the slides. This is the most exciting part, getting the computer hooked up to the system. So, hello. Thank you for having me. My name is Hans. I work for Google doing compiler stuff, especially maintaining the toolchain that we use to build Chromium. I was also the release manager for LLVM for a while, and I worked a lot of on Windows support in LLVM, Clang CL, and that kind of thing. And I've been coming to these for, I think, almost 2 years since I moved to Stockholm. I think I found it through Björn's Twitter, so that's working. And unlike many of you, I'm not super familiar with the latest and greatest C++ 26 features, so I come here to learn and to have fun. But one feature that I do know about is switch statements, because they're old, like me, and I did some work on them in LLVM. So this is a kind of C++ under the hood talk, not the latest features of C++, but under the hood. So let me know if you think you'd like more of these. So we'll try to unpack the title of the talk here, C++ switch statements under the hood in LLVM. There's a lot. So first of all, what is this LLVM business? How many here have heard of LLVM? That's a lot of hands. Very, very cool. Speaking to the right crowd, I guess. So the name used to stand for low-level virtual machine, because at the core it kind of was, or is. It has an assembly-like language, the intermediate representation that you can write programs in, and then you can optimize those and analyze and do stuff with them, and then you can run them. LLVM has a JIT and an interpreter, or you could write out the machine code. But today, then, the name is just LLVM. The letters don't stand for anything. And it's really an umbrella project with a bunch of compiler stuff in it. So it includes libraries for doing optimization, code generation, reading and writing object files of various kinds, and executables. And it contains tools that use those libraries, like compilers and linkers. There's a debugger, various runtime libraries, and so on. And Clang is LLVM C++ compiler, or really C, C++, and Objective-C, and Objective-C++. But there are also many other compilers that use LLVM as a target. I think Intel's C++ compiler uses LLVM these days, and other languages use it too. So Rust, Fortran, Swift, Julia, many others. I think there's Java compilers using LLVM as well. And sometimes we talk about this hourglass model of compilation. So where LLVM sits in the middle, in the sort of the narrow part of the hourglass. And on the left, it can take input from a bunch of different programming languages with compilers that emit LLVM's intermediate representation, or IR. And on the right are all the targets that LLVM can target, generate code for, like the typical CPU architectures, like Intel's x86 and ARM and PowerPC and RISC-V and whatever. And also more exotic things like GPUs and WebAssembly and so on. And also along with the different operating systems and their file formats, their application binary interfaces, and so on. And the beauty of this model is that there's just one LLVM in the middle. So each compiler, like Clang or Rust and so on, they can just target LLVM and don't need to implement all the details of writing this x86 machine code or whatever themselves. And they also don't need to implement all the fancy optimizations that LLVM can provide. So I don't know if I'm cut out to work at things. So this is me drawing the hourglass there. It's a very idealistic image, because in practice, the compiler does need to know some stuff about the target. Like Clang, for example, needs to know how certain C++ things work on ARM versus Intel or Mac versus Windows. And the compiler also often does some optimization on its own, things that are more closely related to the source language, like I think Rust and Swift do this a lot, Clang probably a bit less. And there are also some downsides to this model, like because LLVM can do all this stuff, it's a pretty big project, it's a big dependency. So if you just want to generate x86 as fast as possible, for example, you can probably do this yourself or find a smaller library. But if you also need to support all the other targets and do all the fancy optimizations, then using LLVM can be a good alternative. So that was the LVM part. Now for the switch part, which is the main part. Hopefully you all know about this one. The switch statement in C or C++ has been around for a while. I think it was in C from the beginning. I'm sure it was in C++ from the beginning. You can think of it as a fancy if statement where the code, the computer will jump to different case labels depending on the input, on the switch expression. That's the X in this example. And on the right, we can see how LLVM represents this internally. It actually has a dedicated instruction for this, which is called switch. And we can see here it takes the X as the input, and then it jumps to different labels depending on the value of X. And the label 7 there is special. That's the default label. So if it doesn't match any of the others, it will jump to the default. And here in the C++, we don't have an explicit default label, but there is kind of an implicit one after the switch. Like if the cases don't match, it will jump to the next statement. And I tried to find something new about C++ switches, and there's nothing too much exciting. But there is a common extension, which is supposed to support case ranges, because this is something people use switches for quite a lot. So both GCC and Clang allow this, for example, but it is an extension. This is not standard. But it seems to be on the standards track for C26 maybe, which if it goes in there, maybe it will come to C++ as well at some point. We'll find out. And on the right, we can see the LLVM intermediate representation for this. And you can see it's not very elegant. It has just like exploded the ranges. It doesn't really matter too much. I guess it's memory inefficient and ugly to look at, but it would be nice to do something better there. So that's an opportunity maybe. But LLVM switch instruction is not just used for actual C or C++ switches. It can also be used for other language constructs. So with apologies to the C++ diehards, there's some Rust code here, and it's a match expression, and those can sometimes also become LLVM switch instructions. And that means that when we look at how switches are handled inside LLVM, it actually applies to much more than just the regular switches. So the impact of handling these well is kind of wider. And here is another language construct which isn't a switch at all. It's just a non-fancy if statement. It's a chain of if-elses. But LLVM figures out that it's going to be more efficient to treat this as a switch internally. So it will do that for you if you turn on optimizations. And this goes back to that teaser in this or the question in the teaser for this talk: are switches more efficient than if-else chains? Well, ideally, LLVM will figure out what the best thing is to do, so you can choose to write your code in the way that most naturally describes the functionality you want. So one could say that there may be equivalent, actually. Now, LLVM isn't perfect, so this doesn't always work. So if you really care about performance, you should probably check your output. But this is the idea anyway. And again, the point is that this is not just about literal switches, but also about a larger set of language inputs. So now we know what the switch is. Now let's discuss different kinds of switches. This is a very narrow subject, I feel, but we'll keep drilling. So LLVM really considers two different kinds of switches. The kind on the left, where we actually do different things for the different cases, and the kind on the right, where we don't really do different things, but we just select different values. So in this example, we're selecting a value for the variable y, but this also applies if we're selecting values for multiple variables or for return values and so on. And what LLVM will try to do is it will try to put those values into a lookup table and use the switch expression to index into the table. And that's nice because it means there's no control flow except for possibly a bounce check at the start. So this can be much more efficient than if we have to actually jump somewhere depending on the input. And that bounce check can also be removed depending on the circumstances. The main issue here is the size of the table. So it needs to cover all the cases from the lowest to the highest. And if there are holes, like in this case, we don't have any holes, but if there's also a case 5, for example, we'll have holes for 3 and 4. it will fill those with a default value, if there is one. And if these gaps get really, really big, like if we have a case 1 million there, we'd have a lot of holes, a very big table, and that's not very nice for the binary size. So the LVM, I think the heuristic here is something like there needs to be 3 entries or more for the table, and the table needs to be at least 10% dense, meaning that at least 10% of the slots in the table are populated. And LVM, there's a lot of small tricks that it will do with the table stuff, but one big trick is that it will recognize if the output is actually a linear transformation of the input value, and in that case, it will just emit the instructions to compute it. So saves a lot of space not having to emit a large table there. Like in this example, the output is 42 plus 2 times x. The code will just compute that or return 0 if it's outside the switch range. Yeah.
So this will also happen if you have like a big flag enum or something, because it is always predictable for the next.
If there's a bit flag enum, I'm not sure I understand.
0, 1, 2, 8, like powers of 2 in the value.
Yeah, I think so. Yes. Right. Yeah, that should work. Yeah, and then the multiplication would probably be a shift as well. Okay, but those value selection switches are really a special case. So what about switches in general, where we actually have to jump and do different things for the different cases? So first off, some targets are very special, like and do different things for switches because they have limited or different capabilities. Like GPUs are special, WebAssembly is special, and WebAssembly is kind of funny because we compiled the WebAssembly and then the WebAssembly engine is going to read it and like compile it right to something else. But for the rest of the targets, they will use the following exciting techniques. So before we do anything else, we will cluster adjacent cases together. So if we have case ranges like in the early example using the extension, where several consecutive cases go to the same destination, they will be put into one cluster. So in this example, we have case 0 goes to A, cases 1, 2, and 3 all go to the B label, so we put them in a cluster, and cases 4 and 5 go to the C label, so they become one cluster. And LVM will work with these clusters going forward rather than the individual cases. So that means we're efficient for ranges. It's not that bad as it looked in the beginning. Okay, and once we got them organized into clusters, there are 4 strategies that we use to generate code for them. And we will go through these one by one. So first, if there's just a few clusters, 3 or less, LVM will do straight comparisons. So for a single case, this means we just check if the switch expression matches the case number and jump to the label. So in this example, we check if x equals 0 with the x86 test instruction, and we do a conditional jump. Jump if equals to A. So for clusters with multiple cases, we do a range check. And this ends up being a subtraction of the lower bound, a comparison with the adjusted upper bound, and a conditional jump. So that's just one more instruction than for the single case. And in particular, it's still just one conditional jump, that's kind of the name of the game here. We're trying to minimize the number of conditional jumps. In this example, it's using a LIA instruction to do the subtraction, then the comp, and then the jump if below. The second strategy is a very clever thing it does with bit masks. This slide looks horribly complicated, I think. So if there's a bunch of cases, in this case we have 9 cases, but there's only 3 targets. And so if there's 3 or less targets, it will try to use bit masks to describe the cases. So in this example, for the first one, we create a bit mask for cases 0, 3, and 6 by creating a constant that has the 0th, 3rd, and 6th bit set. So that's 73 in decimal. And then we generate a bit test instruction to check if bit number X in that mask is set, and if so, we jump to the A label. And we do the same thing for the other cases. So with this technique, we can check for a lot of cases with just one bit test, which is, I think, is very elegant. And again, we have to do a range check first to make sure that this is within the range of the cases that we're looking at. And of course, the range has to fit in a machine word for this bit mask technique to work. The third strategy is jump tables. And maybe this is what most people associate with switches. So the idea is that we just put the address of the label, each label in a table, and then we use the switch expression to index into the table and see where we have to jump. This address can be the absolute address, or it can be like an offset, how far to jump. And again, of course, we have to do the range check first. And like the lookup table that we used for value selecting switches, the main concern here is the size of the table. So we need to cover the lowest to the highest case and everything in between. If there are large gaps, we'll end up with a very large table. So again, it uses heuristics to decide when to do this. And the heuristic, I think, is that there needs to be at least 4 case clusters, and the table density needs to be at least 10%. So 10% of the table needs to be filled. And if you're optimizing for size with -OS, it needs to be 40% filled. Finally, when the whole switch doesn't meet the criteria of the previous 3 approaches, so those were kind of limited, right? They had limiting criteria. We fall back to the general solution, which is to build a binary search tree. And that's kind of the classic switch lowering strategy. You look at the case in the middle, see if your value is lower or higher, and then you go left and right in the tree that way. And what's special about LLVM is that it can combine the previous strategies with the binary search tree. So in this example, we have some cases which are suitable for bit tests, some are suitable for jump table, and some are kind of left over, and they're few enough that they will be suitable for straight comparisons. So LLVM uses a kind of bottom-up strategy here, where it will consider the whole set of cases or case clusters. It tries to find the optimal ranges suitable for the different strategies, especially the lookup table. So it tries to find ranges which are dense enough for jump tables. And then it will build the binary search tree around them. So for our example, it will look like this. At the leaves of the tree, we use the previous lowering strategies. And the interior nodes, the orange ones here, are comparisons to traverse the tree. So while the previous strategies, the ones we use at the leaves, these are all constant time complexity, order 1. We're now doing order log n operations for the whole switch. And to achieve that log n complexity, the tree needs to be balanced, right? That's the point. So that normally means we try to put equal amount of stuff to the left and right of each node. But if we have profile information, we can do better. So I don't know if you can read the green numbers on the cases there are profile informations telling us how often these are used. And then we can instead balance on those weights. So in this example, case 70 has much higher weight than the others, and it will be put closer to the top, so we need fewer comparisons and branches to get to that. So although this tree looks slightly unbalanced, it's actually more optimal for this profile, at least. Also, for the straight comparisons, we will, of course, do them in the order of how common the cases are, so most common case first. And that's it, really. Now you know a lot about switches, more than most people, I think. So to summarize, LLVM has a dedicated switch construct. It's used for C and C++ switches, but also possibly for if-else change and for other language constructs, so very powerful. Switches that are used to select values may be lowered without any control flow, except the range check, to table lookups or to linear transformations. Otherwise, switches are lowered as a binary search tree, balanced by profile weight possibly, of straight comparisons, bit tests, and jump tables. That's it. Thank you very much. All right, so I see 2 questions all the way in the back.
Has changes in branch predictors changed how you look to do these optimizations? What's not efficient?
That's a good. So the question was: has changes in branch predictors affected how we do this? It hasn't really. I think the technique is general enough that no, it hasn't. I mean, it may change how some people write their code, but I think this has stayed the same for a long time and hasn't changed. And I can't really think of any change we'd want to do, but that's a good question. Yeah. So that is the thing, that some targets may tweak these heuristics a bit, right? Like when is it most profitable, like what's the right density, and so on. So that's definitely a thing. And also when people compile, like I mentioned that the criteria is different if you're optimizing for size or not. Those are also knobs that, people like to tweak those. Yeah. Next row there.
So you said that the weights are associated with the profile. So I suppose that's both like profile guided optimization, but I suppose that you also take into account like some hints, like if built-in likely or unlikely. Is there any way to express hints like that? If you cannot, like for instance, like if the project is not instrumented for PGO,
right,
and you still want to like indicate that this branch is way more.
Yeah. I'm not sure. I would have to double check what happens when you put likely on a case, for example. I suspect that might. So internally, this might look the same, that it has a high count of frequency, but I would have to double check. In the front, I think.
That was the exact same question.
Okay.
Do you know how the switch implementation compares to GCC switch?
Sorry, I should be repeating the question. How does this compare to what GCC does? So I haven't checked recently, but I think GCC uses the same techniques. I think it does the lookup tables for value switches. It did that before LLVM, so we had to implement that. And I think it uses the same techniques of the jump tables and the bit tests also, and straight comparisons, of course. I think the main difference is I think it can't combine them like LLVM does. I think it will look at the whole thing and like jump table or binary search tree. I think you can construct benchmarks where this matters a lot, but I think in general, probably not a huge deal. So I wouldn't say that one of us has superior, switch performance. Yeah, there was questions over there.
So if you have an architecture where you have different types of jump instructions, like short jumps, long jumps, and so on, is there some way to feed that back into the process, or does that change anything? Or?
Don't think it would change anything for this. That's more a question of like that's more of a code layout problem, right? And it generally tries to lay out the code so that it's close, and then
if you're building a table, jump table, that's more than 256. It's not reachable because this is an actual bug that we have with a compiler that generated short jumps.
Yeah. Well, I don't think the switch lowering code looks at this, right? But other code will be concerned with it. Yeah, there was one. Yeah.
So, if you have a switch case, here you assign the value to a variable per the case.
Yeah.
Will there be a difference if you use the return instruction per case and return the value? No one needs.
Yeah, so the question is there a difference if you're selecting a value for a variable or selecting, like just returning from the cases? So selecting a return value, essentially. No, that's handled the same. Yeah.
What about optimization levels? Does it have any impact whether code is compiled with no optimization, level 1 to something more aggressive?
Yeah.
to control what is being used? And does it affect debuggability?
So, yeah, question is, does the optimization level affect, do we do different things, and does it affect debuggability? So yes, the optimization level matters. If you turn off optimizations, we will do the simplest thing, which I think is just a binary search tree. We will also do this for the value select switches. We will not recognize that they are value select switches. Then I don't think we do different things on, you know, O1, O2, or 3 specifically for switches. It's just optimization on or off. If you optimize for size or not matters for the heuristics, like how dense the jump table needs to be, for example. So that's a difference. And does this affect debuggability? Well, yes, of course. So that's a hard problem. Representing symbolic debug information for optimized code is a tricky one, right? So if you have a big switch with all these cases, and then LLVM recognizes that it's just a linear transformation. If you try to, you know, single step through this program, a lot of the source locations might have become lost. But for the other stuff, I think debuggability should still be good. Like, we will maintain the debug info in the binary search tree. With the jump table, you will jump to your case, and it will have good debug info. So I think it's not too bad for switches. Yeah.
Was perfect hashing ever implemented, like as considered as an implementation?
So the question is, was perfect hashing ever considered as an implementation? That's a good question, and the answer is yes, it was considered. People have tried to do this. I mean, the idea is basically, it's like, if you can't do a jump table because your switch is too sparse, for example, you could compute a perfect hash that like squishes the whole thing into a table. There was a big patch. Someone tried to do this many years ago. It's a bit tricky because, yeah, you have to compute the perfect hash. You also don't have a lot of cycles to. You have to find the perfect hash. That takes some time, and time is expensive. And then you have to compute the hash value at runtime that you're going to use, and you don't have a big budget there. It's like 1 or 2 instructions is okay. You start going beyond that, it's bad. I think that patch also had a lot of complexity. It was a lot of code. It didn't make it through, but yeah, that's definitely a possibility. But it doesn't have it currently. Yeah. All right, thank you.